The aim of this video is to understand the process of wave scattering. Scattering is a general physical process where some form of radiation such as light, sound, or moving particles are forced to deviate from the straight trajectory by one or more paths due to localized non-uniformities in the medium through which they pass. In conventional use, this also includes deviation from reflected radiation from the angle predicted by the law of reflection. Electromagnetic waves are one of the best known and most commonly encountered forms of radiation that undergo scattering. Scattering of light and radio waves is particularly important. Several different aspects of electromagnetic scattering are distinct enough to have conventional names. Major forms of elastic light scattering are Rayleigh scattering and Mie scattering. Inelastic scattering includes Brillouin scattering, Raman scattering, inelastic X-ray, and Compton scattering. Now we will look at some examples of scattering. Of course, the best example of scattering is light being deflected as it passes through air that is filled with particles of some sort. One rather interesting example of scattering causes the sky to appear blue on a clear day. As the sun's light enters our atmosphere, there is always a basic level of scattering caused by the composition of the air itself. This diagram shows the scattering of two lasers. The green laser is scattered more due to dust on the floor. As the laser hits the dust, the light is scattered in many directions. Models of light scattering can be divided into three domains based on a dimensionless size parameter alpha, which is defined as given in the formula. Based on the value of alpha, these domains are alpha much less than 1, which is called Rayleigh scattering, alpha equal to 1, called Mie scattering, and alpha much greater than 1, called as geometric scattering. We used a computational domain of 16 cross 8 as we can't compute for an infinite size domain. But for a finite computational domain, there will be reflections from the boundary. To avoid them, we placed a perfectly matched layer of thickness lambda. A resolution of lambda by 20 is used for the simulation. We used 3 obstacles for checking the 3 different regimes. Now we look at the code used for the simulation. Firstly, we create a 16 cross 8 simulation domain. Next, we implement a perfectly matched layer of thickness 1 unit. Then we create a continuous wave point source located at -7, 0. This point is with reference to the center of the computational domain, which is the origin of simulation. A resolution is set and an obstacle is placed whose size is varied in different parts of the simulation. The simulation is run for 200 time units to ensure that the system reaches steady state. The field values of Ez are stored in every iteration. Electric fields are then plotted for different time instances and a GIF animation file is created. The following is the result of simulation carried out when the object size is much smaller than the wavelength. Because of its size, there isn't much scattering observable. This regime is called Rayleigh scattering and is inversely proportional to the fourth power of wavelength. Orange color of sun in the evening is one of the many phenomena that occurs due to this. Next, we come to the case when the object size is comparable to the source wavelength. This regime is called Mie scattering, where all wavelengths are scattered equally. White color of clouds is because of this scattering. It is also used in cancer detection applications. In the end, we see an object which is much larger than the wavelength. Here, most of the wave is blocked, which forms a shadow in the background. This is called geometric scattering. Ray optics hold true in this regime. In summary, we have identified 3 different regimes of obstacle size in which wave scattering or diffraction take place. The first, when the obstacle size is much smaller than the wavelength and the wave is essentially undisturbed. Second, when the sizes are comparable and diffraction is evident. And third, when the size is larger and the obstacle effectively shadows the wave.